Okay, students, this is section 5.6, Indeterminate Forms and L'Hopital's Rule. You may have learned L'Hopital's Rule in Calculus 1, just depending on what school you went to. I know that our Calculus 1 teacher does teach it in her class, so you may have come across this before. So if not, you're going to learn something very useful that's going to help you with a lot of limits. Alright, so what is an indeterminate form? Well, looking at this example, limit as x approaches negative 1, 2x squared minus 2 over x plus 1, you know if you directly substituted negative 1 in, you would get 0 over 0. So that's our first indeterminate form that we're looking at. We know that we can't evaluate 0 divided by 0. So you can algebraically do this problem by factoring the numerator. So factoring out a 2 would leave you with x squared minus 1, in which that factors to x plus 1 times x minus 1. And then we call that the dividing out technique, where you would cancel the x plus 1's. So you're left with 2 times x minus 1, and now you can substitute the negative 1 in and get negative 4. Alright, the second example, limit as x approaches infinity of 3x squared minus 1 over 2x squared plus 1. So if you just substitute infinity in, you're going to get infinity over infinity. So that's another indeterminate form. Alright, so the way they do this is divide the numerator and denominator by x squared. So you can see you get 3 minus 1 over x squared all over 2 plus 1 over x squared. When you let x approach infinity, 1 over infinity is going to go to 0, so you're left with 3 minus 0 over 2 plus 0, and that's just going to give you 3 over 2. That's also the same thing as if you just looked at your leading coefficients. Since your degrees are both 2, the leading coefficients are 3 over 2, and that's like getting your horizontal asymptote that you would have learned in college algebra. Alright, so what we can do in these cases of indeterminate forms is if you don't have an algebraic way to solve the problem, you can use L'Hopital's rule. It says let f and g be functions that are differentiable on an open interval from a to b containing c except possibly at c itself. Assume that g prime of x is not equal to 0 for all x in the interval a to b except possibly at c itself. If the limit of f of x over g of x as x approaches c produces the indeterminate form 0 over 0, then that limit is also equal to the limit as x approaches c of f prime of x over g prime of x. So what I'm reading is right here. Provided that the limit on the right exists or is infinite. This result also applies when the limit of f of x over g of x as x approaches c produces any one of the indeterminate forms infinity over infinity, negative infinity over infinity, infinity over negative infinity, or negative infinity over over negative infinity. So any type of infinity over another one would produce what we call an indeterminate form. Okay, so those are all the cases where you can use it. So what exactly do? We take the derivative of the numerator and put it over the derivative of the denominator and then try to evaluate your limit. Okay, and if you get back a number, then you're good. Or if you get back 1 over infinity, that would go to 0, so you're okay with that as well. Alright, so remember these cases, the limit as x approaches infinity of 1 over x, so 1 over infinity is going to go to 0. Alright, and then 1 over 0, you should recall this from Cal 1, I hope. 1 over 0 is going to go to infinity, positive or negative, depending on which way you're approaching it and if you have signs involved. Okay, so you may need those two little facts from Cal 1 as well in doing this section. Now you do need to notice that you're not doing the quotient rule Okay, you're just simply taking the derivative of the numerator and putting it over the derivative of the denominator, alright? So just, you're not doing the actual quotient rule, alright, even though it is a quotient. Alright, example 1, evaluate limit as x approaches 0 of e to the 2x minus 1 all over x. So if we try direct substitution, we get e to the 0 minus 1 over 0. E to the 0 is 1, 1 minus 1 is 0. So we can't do that. We don't know what that is, so we're going to use L'Hopital's rule, so always put an LH in parentheses. And so we do the derivative of the numerator. Derivative of e to the 2x is 2e to the 2x. Derivative of negative 1 is 0. And derivative of the denominator x is just a 1. Alright, let's see if we can plug in 0 now. 2e to the 0, and that equals 2. And so we just calculated our limit very easily. Alright, limit as x approaches infinity, natural log of x over x. So think about the natural log of x. As x increases, so does ln of x. So it's going to infinity. And then x itself is going to infinity. So we have an indeterminate form. So we're going to use L'Hopital's rule. Alright, so we're taking the derivative of natural log of x, which is 1 over x. Derivative of x is 1, so of course that's just limit as x approaches infinity of 1 over x. So that would be 1 over infinity, which is going to go to 0. So that was an easy way to calculate the limit. Alright, applying L'Hopital's rule more than once. So we have limit as x approaches negative infinity of x squared over e to the negative x. It's kind of blurry, so I'm just rewriting it. So think about negative infinity squared. So that would change your numbers to positive numbers. So we're going to put positive infinity. And then e to the negative x, well, you're putting in negative big numbers, or negative small numbers, I should say. A negative times a negative is a positive, so you really have e to the infinity in the denominator. So that's the infinity over infinity case. So we can use L'Hopital's. Alright, so limit x approaches negative infinity. Derivative of x squared is 2x. Derivative of e to the negative x is negative e to the negative x. Well, all that does is changes our indeterminate form basically to negative infinity over negative infinity. So we still need to try L'Hopital's again. You can try L'Hopital's as many times as you want, basically, until you get something. So the derivative of 2x is 2. Derivative of the denominator would make that positive e to the negative x. Alright, so now we have a number over e to the positive infinity. The two negatives make a positive. So 2 over infinity, remember a number over infinity is going to go to 0. So that limit is 0. Alright. Example 4. Limit x approaches infinity, e to the negative x times square root of x. Alright, so you have e to the negative infinity basically times the square root of infinity, which that's still going to grow. It just grows slowly, kind of like the natural log. Well, e to the negative infinity is approaching 0. So it's basically the indeterminate form 0 times infinity. So this is not 0, y'all. You can't say that 0 times anything is 0. It is, but that's if you know the number, okay? Infinity is growing bigger and bigger, and remember that e to the negative infinity is approaching 0, but it's not going to ever be 0. Alright, so thinking about your e graph, this is e to the x. Okay, but e to the negative x is the reflection, like that. Alright, so as x is approaching infinity, you could look at it that way. It approaches 0, and then, or you can look at the blue graph as e to the, if you have e to the x, as x approaches negative infinity, so going to the left, then you're approaching 0. You're approaching the axis, but it's never going to be 0. Okay, you've got little bitty fractions in there. So let's see what's going to happen here. What we need to do is change it into the form either 0 over 0 or infinity over infinity so we can use L'Hopital's rule. So what I can do is rewrite this as a quotient. So keep your square root of x on top. This is the easier way to do it. And just flip your e to the negative x and make it e to the x on the bottom. So now you see you have infinity over infinity. Alright, and so we're going to use L'Hopital's. So the derivative of the square root of x, we've done that several times. So 1/2 x to the negative half, derivative of e to the x is e to the x. Let's rewrite that as, we're going to flip 1 over 2 square root of x times e to the x. Alright, so now if we put infinity in, we are going to have infinity in the denominator. So you have 1 over infinity, and so that does go to 0. Alright, so it does kind of make sense that it would go to 0, but you cannot assume that 0 times infinity is 0, okay? Because there are other problems where it does not work out like that. Alright? Alright, limit as x approaches infinity of 1 plus 1 over x to the x. Well, if I plugged in infinity right now, it'd have 1 plus 1 over 0, or sorry, 1 over infinity. 1 over infinity approaches 0. So this is really looking like 1 to the infinity. Alright, well, here again, we cannot assume that 1 to any number is 1. Yes, it is if you know what the number is, if it's a real number, but infinity is not, it's a concept. And you have to remember also that this is approaching 1, it doesn't equal 1. 1 over x is approaching 0, so it's never going to be 0. So you're talking about like 1.000 something raised to the infinity. Okay, well, raised to a really big number, remember this x is your exponent. So think about if you just took something like 1.001 and raised it to the 100, so to speak. That's going to be a number. That's not going to be 1. Alright? So the way we do this, we've done something similar. We're going to use an equation. We're going to call this y equals the limit as x approaches infinity. Similar to logarithmic differentiation. Okay, so we're going to take the natural log of y, and then you can put your limit first and put the ln after that. Natural log of 1 plus 1 over x to the x, and you can probably guess what comes next. So I'm just going to draw an arrow, use some of the right side of the board. Alright, so what comes next is using your properties of the logs. Bring your x down. So x times natural log of 1 plus 1 over x. Well, as you can see, we don't really have the indeterminate form. We do have an indeterminate form, but it's like infinity times 0, which we did before. We need to write it as a quotient in order to use L'Hopital's rule. So the way that we can do that is we're just going to take this x here and flip it to the bottom and call it 1 over x. So I'm going to go back over here to the left side of the board. So ln of y equals limit x approaches infinity. And we're going to keep natural log of 1 plus 1 over x on top and flip our x and make it 1 over x on the bottom. Alright, so now if you look at plugging in infinity, you have natural log of 1 on top, and then 1 over infinity. Natural log of 1 is 0. 1 over infinity goes to 0. So we do have it in the form where we can use L'Hopital's rule. Okay? So ln of y, so to calculate our limit, we need the derivative of the numerator. So derivative of natural log of 1 plus 1 over x is du over u. Our u is 1 plus 1 over x, so our du would be negative x to the negative 2. And then over 1 plus 1 over x. Okay, so this is, I'm going to label this f prime of x over, and now I'm going to do g prime of x on the bottom, and that's negative x to the negative 2. Okay, so it's a complex fraction. It's looking kind of complicated, so how about we do it this way? Let's flip and multiply and see if we can evaluate this. So limit x approaches infinity. So think we had negative 1 over x squared, and then let's see, negative 1 over x squared. That 1 plus 1 over x would actually be part of that quotient. My negative 1 looks funny, so I'm going to fix it. Alright, there we go. Alright, your denominator is also negative 1 over x squared. We would flip that and multiply by the reciprocal, so negative x squared over 1. Okay? So limit as x approaches infinity. Well, we can use algebra. The negative x squared and the x squared cancels. Really, we have a positive now, negative times a negative. So let's see what we have. Natural log of y, which is on the left side. So can we calculate our limit? Well, we have 1 over 1 plus 1 over x. So let's see, as x approaches infinity, 1 over infinity goes to 0. So it looks like we're just left with 1 over 1. 1 over 1, so that's just 1. Alright, so remember we want to get back to y, and so we would take our base of the natural log, which is e, so y would equal e to the first power, which equals e. Alright, so that tells me that that limit is e. I think I've done that before in this class with y'all, so you've seen that before. The limit as x approaches infinity of 1 plus 1 over x to the x is equal to e. Alright, and that is one of the definitions of e, or one way that you can prove e, basically. Alright. This one is similar because you see you have x as an exponent, so it's the limit as x approaches 0 from the right of sine x to the x. Alright, so this is 0 to the 0, which is indeterminate, but it's not in the form that we can use L'Hopital's rule. So we're going to have to let y equal this limit. And let's go ahead and at the same time take the natural log of both sides. So limit as x approaches 0 from the right would be ln of sine x to the x. So ln y equals limit x approaches 0 from the right, bring down your x, times natural log of sine x. Okay, so let's look at this. So the natural log of sine of 0 is 0. You can't take the natural log of 0, it's undefined, okay, because your domain is x is greater than 0. But if you look at your natural log function, let's just see what it's approaching. Alright, so as x approaches 0 from the right, the natural log is going to negative infinity. So it looks like this expression would be approaching negative infinity, and then of course 0 times that. So we still have an indeterminate form here. Alright, so let's go ahead and rewrite it to where we can use our L'Hopital's rule. So ln of y So let's keep ln of sine x in the numerator and drop the x and make it 1 over x in the denominator. So now we see we have negative infinity over, and then this would be positive infinity, 1 over 0 as it approaches 0 from the right. So we can use L'Hopital's since it's in quotient form now. Okay, so we're going to take the derivative of the numerator and denominator. So derivative of natural log of sine x, so du over u. Derivative of sine is cosine, back over the u, which is sine. And then derivative of your denominator, which is x to the negative 1, would be negative 1 over x squared. I think it's better to write it that way. It's easier to comprehend like that instead of the negative exponent. Alright, so let's see. If you kept the 0, or if you plugged in the 0, so to speak, 0, cosine of 0 is 1, but sine of 0 is 0. So you still have basically infinity over infinity, okay? What we can do now, let's rewrite this as cotangent. Okay? Now, this is just going to be like a little trick, basically. Think about the reciprocal of cotangent, which is tangent. So what we can do is we can flip the denominator, which is going to bring that x squared up and make it negative x squared, and flip our numerator and just call it tangent x on the bottom. So we're rewriting cotangent x as 1 over tangent, and we're rewriting the denominator just basically flipping and multiplying by the reciprocal, okay? So we end up with negative x squared over tan x. That's just easier to plug in the 0. Now you can see you would get 0 over 0, tangent of 0 is 0. So let's use L'Hopital's again and see if we can get somewhere. Now remember, this is still equal to ln y on the left side. I just haven't brought that down. Alright, so the derivative of negative x squared is negative 2x. Derivative of tangent is secant squared of x. So let's see if we can plug in 0 now. So we get 0 in the numerator. Well, secant of 0 is 1 because it's the reciprocal of cosine, and cosine of 0 is 1. 1 squared is 1. So we do get 0. So we got somewhere. Remember though, this is natural log of y is equal to 0. And so that means y would equal e to the 0, which equals 1. Okay, so since we let y equal that limit at the very beginning, then that tells me that my limit is equal to 1. Okay, and if you remember, well, I'm trying to think if we learned that in Calculus 1 as one of the special limits. I don't think we did, actually. So that's a new limit. Sine x to the x, limit as x approaches 0 from the right, is equal to 1. Alright, thanks for listening.